today we're going to be talking about binomial distributions. Okay, so far we've been talking about discrete probability distributions, these models of what the probability space of all the samples, of all the different outcomes will look like. Now, the binomial distribution is a special case of these discrete probability distributions. Binomial is 1 out of 2, and so we're going to be talking about this special case because this actually ends up being one of the most frequent probability distributions that you end up using. And in binomial distributions, what you're particularly interested in is this, 1 out of 2 outcomes, like heads or tails, or black or white, 1 out of 2 things, right? And how many successes, which we call K number of successes in n trials. So something like how many heads out of 10 tosses. Then we're going to do a quick review of the multiplicative rule, because that's going to be important for dealing with discrete probability distributions in a binomial way. How many outcomes with K successes? There's going to be a formula that you could use to figure this out real quickly. And then we're going to talk about probabilities in a binomial distribution. So how do we actually get the spread of all those probabilities? And in such a distribution, how do we find expected value, and how do we find the standard deviation? Okay. All right. So discrete probability distributions, as you know, these deal with outcomes that are nameable and countable. So, there aren't an infinite number of possible outcomes. There's a discrete, finite number of them. So your sample space is all the outcomes, right? Just flat out all the outcomes. But the probability distribution is taking that sample space and also finding the corresponding probabilities. But frequently, one of the most frequent probability distributions you'll run across is the binomial distribution. So it's really good to be familiar with this particular one and all of its quirks and foibles. All right, so let's talk about this binomial distribution. So many random variables, they're really counting the number of successes in n independent trials. So by successes, we don't necessarily mean that it has to be like a winning trial or anything. It just means whatever you're interested in, right? Whatever outcome out of 2 outcomes you're interested in. A lot of times the random variable is counting how many times that interesting event happens in n number of trials. So let's say we have 20 independent trials. We could have 0 successes, 1, 2, 3, 4, 5, all the way up to 20, right? So that would be, so the number of successes would be our K value, and K can range from 0 to 20. So just to give you examples of some, it might be counting the number of heads in a random sample of 10 flips of the coin. So here the random variable x is a number of heads, right? Another example is counting the number of children who have been diagnosed as autistic in a random sample of 1,000 children. So here, in this case, the random variable x is number of children diagnosed with autism. All right. And another example is counting the number of defective items in a sample of 20 items. So notice that, when you think of the word defective, you don't really think of that as successes. But it's really what we're doing is we're counting some outcome of interest for every n trials. In this case, n is 20, right? So here, x equals number of defective items. And just to round it out, let's talk about what the n is here. So n, in this case, is 10. N in this case is 1,000. And n in this case is 20. Right? So let's think about why these are called binomial situations. So in each of these situations, you either have a success, the event of interest, or you have a failure. It's not an event of interest. So here, what we would see is that there's in all of these different situations, there are two outcomes that you could have. You could either have a head or a tail, and they both have some probability, and those probabilities add up to 1, right? It has to, because you only have those two choices. There's here, it's either being diagnosed as the probability of being diagnosed as autistic and the probability of not getting that diagnosis. There's only those two outcomes. And here, it's either being defective or not being defective. It's one other of those two outcomes. So these are binomial situations because there's two outcomes that are disjoint, right? So it's one or the other, right? And if you add the probabilities of those outcomes, so if you add the probability of outcome 1, right, plus the probability of not outcome 1, right? So the other one, then you should get 1. And so another way to put it is the probability of one outcome, outcome 1, is equal to 1 minus the probability of not that outcome, right? So that's the other way you could think about this. All right, so now let's briefly review the multiplicative rule. Remember when you had to think about things like this, where the proportion of adults in the U.S. with at least a bachelor's degree is 29%. Suppose you pick 4 adults at random. What is the probability that exactly 2 have a bachelor's degree? And some of the things that we did in order to find these probabilities is we imagined having, slots for these different adults. And you either have the probability of getting the master's degree, right? So let's say these two get the 29, right? Or you have the probability of not having the master's degree, the other outcome, right? So that would be the flip side, the 1 minus 0.29, so that would be 71, right? So this is one combination. So, but this would be that they would have bachelor, bachelor, no bachelor, no bachelor, right? But then there are other combinations of exactly 2 having a bachelor's degree, right? And so you'll have to find those other combinations as well, like B, N, B, N, or B, N, B, right? And so on and so forth, right? But just to recap the multiplicative rule, in order to find this particular guy's outcome, right, we would have to multiply these together, these probabilities together. Now, I want you to notice something. We're not actually going to do this problem. We've done it before. But I want you to notice that, let's say we wanted to find the probability of getting this particular outcome. Although the order will change, in multiplication, it doesn't really matter what order it is. So this value is exactly equal. So this, the probability of this outcome is exactly equal to the probability of this outcome, right? And that's going to be important for us to keep in mind, right? And I just want you to realize that, we are multiplying these probabilities together. Now, just to remind ourselves a little bit more about the multiplicative rule. Now, it's much more likely that that if you picked a random adult, they would not have a bachelor's degree, right? So which of these combinations is more likely, right? all 4 people having bachelor's degrees or none of them having bachelor's degrees? Well, if you just think about, the fact that, only 29% of adults in the U.S. have at least a bachelor's degree, you're going to know that this combination of all 4 having a bachelor's degree is much less likely than all of them not having a bachelor's degree, right? And that makes sense here, and these probabilities bear witness to that. All right. So before we use the multiplicative rule, it's going to be handy for us to know exactly how many outcomes with k successes we'll find. So far, we've been looking at relatively small sample spaces. So maybe out of 3 coin tosses, how many have exactly 2 heads? In those kind of cases, we could actually list out all the possible outcomes and then just count how many of these outcomes have only 2 heads. But as soon as the sample space gets a little bit bigger, like 6 tosses, 7 tosses, that's 2 to the 6th power, 2 to the 7th power. And, they don't call it growing exponentially for nothing, like those numbers get really big really fast. So if you think about 10 coin tosses and how many of those outcomes have exactly 2 heads, that's going to be way impossible for us to actually manually draw out. So there is a shortcut, but before I teach you the shortcut, I do want you to see how it fits together with the manual way of doing it. So I'm going to use this example, the bachelor's degree one, and here's what you're going to see. Here we have the manual list of outcomes, and so here's I'll have to draw it in sort of 2 big columns, right? So here's person number 1, number 2, 3, and 4, right? And then I'm going to draw another list for 1, 2, 3, and 4. It's just that we know we need, it's going to be 2 to the 4th power, and that's 16, and so I'm going to draw 8 in each column. All right, so here, we're going to just start off with half of these outcomes, the first person has a bachelor's degree. Half of these outcomes, the first person does not have a bachelor's degree. And then half of these, the second person has a bachelor's degree. Oops. And then half of these as well, the second person has a bachelor's degree. Okay, and then, see, already with 4, it gets to be quite a bit. Can you imagine doing 5? Almost there. Okay, there we go. So that's our entire sample space of all the different outcomes. Now, each of these outcomes are not equally probable. It's not like heads and tails, right? But we know that this outcome is much less probable than this one. This one is also much less probable than this one, right? So we know that they're not all even, but this is at least the list of all the possible outcomes. And now we want to know, what is the probability that exactly 3 will have a bachelor's degree? Well, it helps to know how many of these outcomes have at least 3 that have a bachelor's degree, right? So let's see. This one has at least 3 that has a bachelor's. This one, this one, this one, and that's it, right? So 4 out of 16, right, have at least 4 out of 16 of the outcomes have at least 3 people who have a bachelor's degree. Now, this does not mean that the probability that exactly 3 have a bachelor's degree is 4 out of 16, right? Because each of these are not equally probable. But it's good to know how many of them there are, right? Now, there is a shortcut to get this number of 4. How many outcomes with k successes? And here, k is 3, and n is 4, right? Out of 4 adults. So let's put that here. N is total number of trials, or total number of spots, right? Number of independent trials. And k is number of successes, right? Generally. In this case, k